So hello everybody, my name is Olaf Günnewig, I'm Head of Business Development at Dayondo. Dayondo is a leading manufacturer of industrial computerized tomography systems for non-destructive testing. Maybe some of you remembered our podiums discussion last year on rocket engines. And if you think about rocket engines, you think these are really high temperatures in rocket engines. So we're discussing about metal alloys like nickel-based alloys, for example, Inconel, or copper-based alloys, GR-COP42, for example. Yeah, but now imagine applications where the temperatures are higher, as in rocket engines, for example. Yeah, this is a wonderful world of ceramics and ceramic matrix composites. And these are wonderful materials. On the one hand, they resist very high temperatures, up to 3000 degrees. On the other hand, they are a little bit flexible. That means you can put a nail through the ceramic. Try this with your coffee cup. I think it's not the best thing to do. And so I was in discussion with IPM. What's interesting for you in these harsh environments? And I said, we have to make a masterclass on ceramics and ceramic composites. And this is what we would like to present to you now. And now I give to Danny. Danny will introduce the speakers.
All right, thank you, Olaf. Danny Schippel, I'm working for the Composite United. We are an industrial association with around 400 members, 400 companies and research institutes, and around 70 of them deal with those fiber-reinforced ceramics, so-called ceramic matrix composites. And I'm the head of that division that deals with that. And today we have 30 excellent speakers, starting with Fabia from the German Aerospace Center in Stuttgart. Then we have Gotthard Nauditt from Schunk and Stephan Schmidt-Wimmer from the Ariane group. And we kind of set three talks around the entire process chain to give you a little idea what those materials are for, how they're built or created, and what does that actually have to do with additive manufacturing. All right, I would say we start, and Fabia, the stage is yours.
Thank you, Danny, for the introduction. Today, I present to you the activities of my department in the field of ceramic matrix composites, especially the complex shaping of CMC components. The DLR has 30 institutes all over Germany with more than 10,000 employees. My Institute of Structures and Design is located in Stuttgart. In my department, Ceramic, Composites and Structures, we are 20 employees. Our expertise in the CMC field lies in the material development, the design and manufacturing of prototypes, the characterization of components and materials, and the finite element modeling, as well as simulation of structures and processes. The equipment for the manufacturing includes several high-temperature furnaces, a high-temperature autoclave, resin transfer molding devices, a hot press, filament mining machines, and a 3D printer. For the characterization, we use full-scale CT analysis, SEM, X-ray diffraction techniques, and thermal and mechanical analyses. But first of all, what are those so-called CMC materials? CMC stands for Ceramic Matrix Composites, which describes fiber-reinforced ceramics. With this concept, we can combine the excellent properties of monolithic ceramics, such as high temperature resistance, with the ductility of fibers. Typically, we use fibers like carbon fibers or ceramic fibers like silicon carbide and aluminum oxide. The ceramic matrix consists of silicon carbide, carbon, or aluminum oxide as well. CMC show very damage-tolerant fracture behavior, while their density is very low. High temperature stability as well as thermal shock stability and a good abrasion resistance as well as high hardness are the key properties. CMC applications at DLR cover the fields of space, aviation, energy and mobility. Examples are lightweight structures for satellites with a very low expansion, CC6 nozzles and rocket tips for sounding rockets, turbine vanes for aircraft engines, 3D printed CSIC components for heat exchangers, for example, ceramic brake discs for planes and cars, and full CMC piston rings for hydrogen-powered piston engines. All these applications require different material properties. That's why DLR has a portfolio of different CMC materials. The carbon fiber-based CC6 material has a carbon silicon carbide matrix and is manufactured with the reactive melt and filtration, the so-called LSI process. High application temperatures up to 1600 degrees C are possible for short and medium-term use. For even higher temperatures, around 2000 degrees C, we develop ultra-high temperature CMC. They consist of pitch-based carbon fibers with a high temperature resistant zirconium diboride or zirconium carbide matrix. For the use in aircraft engines with a very long service life, we develop 6.6 CMCs. Thereby, silicon carbide fibers are used instead of carbon fibers due to their improved oxidation resistance. Another CMC class are oxide CMCs based on aluminum oxide fibers. In our department at DLR, we combine them with a polymer-derived silicon oxycarbide matrix for temperatures around 1100 degrees C in long-term use. The before-mentioned liquid silicon infiltration process, LSI, starts with the shaping of the green body. Fibers are integrated into a polymeric matrix. Then, pyrolysis leads to the conversion of the polymeric matrix into a porous carbon matrix. Finally, in the reactive melt and filtration step, a liquid melts from silicon or zirconium alloys, for example, is infiltrated into the porous component. And then, for example, silicon can react with the carbon, forming the silicon carbide matrix. The whole CMC manufacturing is based on near net shape additive manufacturing techniques. The preforming techniques are based on filament winding techniques for rotational symmetric tubes or nozzle structures, resin transfer molding of fiber preforms to achieve a very small radius in radomes, for example, hot pressing of ceramic brake discs, and the 3D printing of complex-shaped C6 ceramics for heat exchangers or satellite sandwich structures. The 3D printing was developed and improved together with Schunk carbon technologies in the Brodenker project. For the 3D printing at DLR, we use a pellet-based printer. First of all stands the compound development. Granules of thermoplastic binder are melted, and suitable fillers like carbon black silicon carbide powder, activated carbon, or short carbon fibers are added. All the components are mixed in a twin screw extruder and then extruded as a filament, cooled in water or air, and cut into pellets. For the component manufacturing, these compound pellets serve as a feedstock for the extrusion-based 3D printing. In contrast to the described LSI standard process, we add additional chemical debinding after the shaping of the green body. Then the conversion to SiSiC happens in the final liquid silicon infiltration step. Different feedstocks lead to different microstructures. For example, with this feedstock, we can achieve almost pure silicon carbide with no excess carbon and only 12% remaining silicon. At DLR, together with our colleagues from Cologne and Göttingen, we are able to cover the full process chain of the design and manufacturing of complex-shaped CMC components. This is shown at an example of the Tradizerator project, where CMC turbine vanes were designed and manufactured. It all starts with the manufacturing of a suitable CMC material. Then, the redesign of the former metallic components is needed. Here, for example, the external geometry was adapted and a new cooling system was designed. Special toolings were fabricated, and after the successful manufacturing of turbine vanes, we added a grinding step of the outer surface to meet the high requirements for surface roughness, which comes from aerodynamics. Then laser-drilled cooling holes are integrated in the trailing edge, and the whole process is accompanied by stress analysis at different operating points. So we coupled CFD and FEA calculations for the stress calculations. Then, finally, DLR has the possibility to actually test the components in several wind tunnels to evaluate their performance and their cooling efficiency. So if you're interested in our CMC material or in a joint project cooperation, please do contact us. And now I hand over to my colleague, Gotthard Nauditt from Schunk Carbon Technologies, and he will tell you more about the 3D printing of ceramics.
Yeah, thank you, Fabia. Good afternoon to you all. I hope you had a really good conference so far. I really enjoyed it. I had some inspirations here, and I like this. And I hope I can give you also some inspiration in the next 10 minutes when I'm talking about the additive manufacturing of ceramics and about ceramics matrix composites. Let me say a few sentences to the company. Schunk Group has not to be confused with the Schunk gripper and clamping system. I was asked many times here. We are the Schunk Group. We have 65 locations worldwide and in 26 countries, and I have 9,199 nice colleagues. And we contribute to a turnover of 1.5 billion. And no fear, I'm not going to any of these applications. We have a very widespread applications and products. So if you're interested, I just advise you to step by our webpage, schunk-group.com. You will get tons of information there. I am working at the headquarters in Heuchelheim in Germany as an engineer for fiber reinforced materials, especially for CMCs. And we are producing them in Heuchelheim, like here shown, for example, the white ones. That's as Fabia already showed us, an oxide fiber reinforced oxide ceramics. So we have an aluminum oxide fiber embedded in an aluminum oxide matrix. Or the gray or dark ones, that's a carbon. That means it's a carbon fiber placed inside of a carbon matrix. And what's the beauty of this product, of this material? The carbon-carbon, for example, you can heat up to 3000 degrees C as long as there is no air present. And it has a very low density. And even there is no creepage, like you know, for example, with many metals, they begin to creep. Carbon-carbon will not, even at temperatures of 1800 degrees C. And yeah, we of course are printing also a lot. I implemented a 3D printing service center at our headquarters in Heuchelheim in order to provide my colleagues printed part with polymers. And so sometimes I said, yeah, maybe we should try to do some printing in the direction of continuous fiber reinforced materials in order to convert them into ceramics. And as you can see, yeah, we started a project together with the Technical University in Dresden. There was a tool head developed which was able to extrude carbon fiber tapes, carbon fiber tape material. We printed, for example, here the carbon fiber peak material, and yeah, it worked. But we saw, and you're not looking at a kind of slow-mo here, you're looking at the real time, and it was slow, and we very fast encountered a lot of other problems where we said, okay, it was interesting, but maybe we should stop here. It's not our core business to create printers here. Maybe we should wait what the market will give us. And so at that point, I here collected some of the companies that are handling with carbon fibers, with continuous fiber reinforcement, not with the short fibers. If you look at the top to the right, the APS, Mark 3D, Anisoprint, 90 Labs, they are all printing in a gantry system, X and Y, with the fiber reinforcement. The 90 Labs also are using a kind of post-processing where they do a compression of the printed part afterwards in a mold in order to increase the properties, to reduce the porosity. And the other companies here, this list is not exhaustive, I have to say this, there might be more or less. The other companies here, from Mantis Composites to Arrivo, all they are using robotic placement systems. And for example, what I found at electroimpact.com at their webpage, this is a really impressive 3D printing method. You print your mold and you lay your fibers outside of it in all room directions, not only in X and Y direction. You can change the angles and you get a more, a better part. So, and nevertheless, all these processes, they are pretty cool, and they are tailored for CFRP, for carbon fiber reinforced polymers, not for CMC. So still we are looking and we are waiting. And meanwhile, we invented a really good technology, which for us was really a game-changing technology. We are printing reaction-bonded silicon carbide. And to do this, we use a powder bed printing process with binder jetting. I think you all know this process. We are using silicon carbide powder for this. Silicon carbide powder grains. And an organic binder is then printed inside of these grains to build the part. The beauty of the powder bed process is you can scale it really easy. Yeah, we can have big dimensions, and right now we are able to print 1.8 by 1 meter in footprint and build area, and we can print 85 liters per hour, which is quite fast. So it gives us a high flexibility and a good print rate. Of course, we have a limited resolution of 300 microns because of the powder, which gives a rougher surface. But the process, if you look at it, it's a process flow. The beauty is here we have another shaping process. Of course, we have the traditional processes like an isostatic pressing or a slip casting, but the 3D printing just stands in row with these shaping processes because the whole post-treatment is just the same as the other processes. So we don't need to have any special treatment for the 3D printed part. We just use the furnaces, etc., that we have already, and we can even put all the parts in one furnace. So what is then done afterwards? We do a pyrolysis of the printed part. In the pyrolysis, the binder is converted from the organic into a porous carbon. Fabia already explained it. Then there takes place a siliconizing. That means the melted silicon is getting inside of the part by capillary forces and reacts with the present porous carbon and forms a secondary silicon carbide around the primary silicon carbide grains. And this leads us to the right-hand side to the microstructure where we have dark gray grains. This is the primary silicon carbide, our powder. Around that we have light gray areas, which is the secondary silicon carbide, and the pores there are filled with the free silicon. The free silicon remains in the pores. And this gives us a very stiff material. If you look at the value, 380 gigapascal, that's quite good. And it makes it predetermined, for example, if you look to the upper right, for an application like this frame structure. This frame structure carries a very heavy load or a heavy load in a process and provides good stability and high precision. And this frame structure is printed in one part. And you cannot manufacture it in traditional way in silicon carbide. So this was our game changer in this application. Of course, you can do ballistic protection with this technique also. That we do, for example, for helicopter seats, the back, or even radiant tubes with inner rippings for better heat transfer, etc. And yeah, that's already gets me to my conclusions. Printing of ceramics, of monolithic ceramics, I think I could show is quite state-of-the-art. We have our intrinsic. We're using the powder bed process. And on the other hand, with the CF3D, the continuous fiber 3D printing, there is a lot of cool stuff available, cool techniques available. And we are still observing and seeing if we at some times can change to such a production process. Meanwhile, we are still manufacturing it like Fabia explained with RTM or pressing or winding. And nevertheless, we are continuing our material development for the 3D printing with carbon-based materials because we think the 3D printing really enables us to develop new materials and to encounter new designs or new products. So far, I thank you very much. This was quite the ground, and we're getting now over to the rocket science. I'm handing over to Stephan.
Okay. Okay, thank you. So I will tell you something about additive manufactured CMC for space applications. I come from Ariane Group, just a short background on it. Ariane Group is a joint venture, 50-50, out of Airbus Group and Safran in France. And we work on all the topics of space transportation, defense application, and equipment services in the area of spacecraft, space launchers, all that. I think the most known product from Ariane Group is the Ariane launcher. Now we are waiting all for the launch of Ariane 6, which is promised to second or third quarter in 2024. We hope for it. And we are working with 8,300 employees on different locations in Europe, so in Germany, several in France, and our launch pad in French Guiana in Kourou. So Ariane Group, I'm a guy from the old space, not from the new space, and that's why we have up to 25, maybe 30 years of experience in the area of CMC manufacturing, which is a kind of generative processing or additive processing. And yeah, we did a lot in this area. We worked on components up to a TRL of 9, meaning they are space proven. And what we are doing in Ottobrunn is really we focus on prototype manufacturing, on manufacturing of demonstrators up to the prototype, and then do a transfer of these technologies to the business units of Ariane Group who are in the manufacturing cycle. or in the production cycle. So, as the previous speakers already told you, ceramic matrix composites are, for me, really an outstanding material. I work on this topic since, I think, 30 years now, and it's again and again interesting. For me, the most impressive characteristics are really, on the one hand, damage tolerance. So Olaf, you just mentioned the part here. So you can really penetrate this fiber-reinforced ceramic with nails, and nothing happens. It reacts or behaves like wood. Temperature resistance, very, very high temperatures, meaning up to 2000 degrees C, in combination with thermoshock resistance you see here, because you can imagine if you have the boost of a rocket motor, of a propulsion system, in some milliseconds you are from 0 or below 0 up to maybe 2800, 2900 degrees C in the wall. And one additional benefit, because of the low density, is the lightweight design of the components. So what we're doing in Ottobrunn, that's where I'm working, or where the high temperature materials lab is located. We have the full process chains available, from incoming inspection of raw materials till the outgoing quality inspection or quality assurance of the components. So we work on textile preforming, we work on infiltration and coating technology, we work on high temperature processing. We have a lot of facilities available, I will show you in one of the next slides. And we do quality inspection also with computer tomographic inspection systems. And we do the evaluation of this computer tomographic data ourselves in our offices. Okay, so what you see here is our new technical center. It was inaugurated in 2022. You see all our facilities are computer-based or computer-aided robot-based, because what is our intention is really to have it as near as possible on the industrial application or on the industrial manufacturing later on. And same for all the oven technology, which is all computer-aided. So these are high temperature ovens. You can go up to 2000, 2200 degrees C to do the ceramization of the parts we are building. We work in different applications. On the one hand, core business of Ariane Group in Ottobrunn is building of propulsion system, of combustion chambers and nozzles. Here we did something in the past. We work on thermostable assembly structures with a CTE close to 0 in a big temperature range. We work on orbital thrusters, missiles, because technology for small missiles, for propulsion systems, is quite similar to technology for a big launcher. And what is our main program at the moment, or our main work at the moment, is work on hypersonics for defense application, hypersonic application, in the field of propulsion, in the field of structural parts, and so on. We work only, or more or less only, with black CMCs, meaning non-oxide CMCs. So we have a wet filament winding unit, robot-assisted, as I told you. We do curing, pyrolysis, re-infiltration, or ceramization linked to the characteristic of the material. We do this several times, and we create a real carbon SiC, which is very, very resistant to oxidation and temperature, very high temperature, and with that, with very, very good mechanical characteristics at high temperature. Here we do nozzles, thermal protection systems for re-entry. We do adapters, nuts, bolts in carbon SiC, because you have these parts, for example, these fuel injectors you see on the upper right, in a very, very critical temperature range. We do thermostable structures, air-breathing propulsion, and orbital propulsion with this kind of material. Another material is carbon-carbon SiC, quite similar to the DLR material. There we work on textile technologies, very known, and we do a 2D structure via braiding, and if we need a reinforcement in the third direction, we do a sewing process, meaning tufting, stabilizing, because then we can do the further ceramization or densification without any tooling. And then, if needed, we do a slurry coating of an environmental barrier coating on the outside or the inside, linked to the application of the part, followed by a siliconization, meaning a high temperature process where you do a conversion of this slurry coating. Here, our main business is at the moment building up hypersonic propulsion structures here the big point was we work at temperatures beyond 2000 degrees C in the combustion area, and also here a ceramic will not withstand this structure, or not this structure, these temperatures in the combustion area, and that's why we work with active cooled ceramics. Something very new, very, yes, difficult or tricky structure. We create cooling area in the textile technology or during the textile processing, and then do the ceramization, and afterwards we have an active cooled ceramic part which can really work at these temperature regimes. I'm talking to you about 2000, 2200 degrees C, something like that. But we also worked a little bit, to be honest, on really 3D printing, additive manufacturing. Here a colleague of mine did a small development program made out of short fiber reinforced CMCs. If we need higher strength of this kind of material, we can do a reinforcement via back structure by our textile processing. And here we developed, quite similar to the DLR approach, fiber granules or granulates based on phenolic resin, printed to preforms, pyrolyzed, and all this was done in the powder bed processing. The last step was then a liquid silicone infiltration to create out of this carbon-carbon material a carbon-SiC material. And as you said, we did, or as you see, you see nozzle extension, kind of a combustion chamber, mirrors. That's what we did with this kind of processing. Okay. And also, I think you're well aware, because some colleagues of mine were on this forum here last year, also on the Formnext they presented. We also do a lot of work in the area of product development for aerospace applications in the area of metals. That's absolutely not my business, so I'm not the expert here. But what we have in Ottobrunn and also in Vernon, close to Paris, are several facilities from EOS, and they are all equipped with optical tomography system for the in-process monitoring. And yeah, up to now we have really qualified components, especially for Ariane 6, and we work also on parts for the successor of Ariane 6, whatever it will be. That's it so far. This is the team working in Ottobrunn on CMCs, the name of the lab. And if you have any questions, I will finish here and hand over to Danny, Olaf, whoever. Thank you.
Thank you, all the speakers. Olaf, we prattled back and forth. I suppose, if you're okay with that, I would like to start. I've gathered some questions from the audience before our talks. I would like to pass them. Starting maybe with the rocket science, Stephan. Those 3D structures, those active cooled structures, which were probably single use for a couple of minutes, those defense structures, are you seeing a way of transferring those materials to other fields of application?
As long as it's an application working in high temperature environment, harsh environment, yeah, you can use it for every application you want to have. If you have these really, really high temperatures and you need good performing material in this area of temperature.
Okay.
So sure.
Okay. Whoops. Okay, there's also a question. What material do you consider as the most promising for the future under the aspects of serial production, low costs, etc.? Who can answer?
That is a question.
Not me, because I'm not a specialist of low cost.
Either.
The most promising future serial production. Well, we have a couple, maybe I answer that if that is okay for you. We have a couple of serial production applications already in the fields of CMC. Most of them you have all been using without knowing the brakes of commercial aircrafts, for example. They're made out of CMC, and we have a production scale, I think it's around 40,000 brake discs manufactured per year, so that is a very high volume application. And there's a lot of going on in terms of how to optimize those technologies to make it cheaper. And when we talk about costs, those costs came down the past years. We can go to other applications, for example, in terms of maybe Fabia. That's one question I could pass already to you. That's very similar to that. You talked a little bit about Six Sig, for example, which is used in engines for aircrafts. For example, if you if you have an Airbus A320, which is similar to the Golf in automotive, like the standard aircraft you have in the air, half of those engines already use Six Sig materials, have not. Can you elaborate why Six Sig is used, for example, in there?
So Six Sig is not a low-cost material, but in this case, we can really benefit from the material, and it's worth the costs, because we can make the engine lighter, we can burn at higher temperatures, which leads to efficiency improvements and therefore reduction in specific fuel consumption, which means a reduction of CO2 emissions directly. And this is a topic which is very important in the future, and I think there are many applications where Six Sig or also other CMCs can be used.
If I understand correctly, while using Six Sig and those LEAP engines from, in this case, General Electric is the manufacturer, we either save a lot of fuel, which leads directly to savings of CO2 emissions, or, if I understand correctly, please comment on that, we fly faster, or we can burn at higher temperatures, correct?
Yes, of course, especially in military applications, we can also benefit from this.
We have, I guess, 1 more minute. Time for 1 or 2 more questions.
Okay, there's another question. What types of materials developed through AM are proving most effective in extreme environments, such as high temperature, corrosive atmospheres, or the vacuum of space?
I didn't understand the question. What types of materials do you...
Yeah, but it's always linked to the application. If I have short-term application, I think for me the most promising material is carbon-thick. If we have long-term application and not that extreme temperature, it will be silicon carbide, reinforced silicon carbide, yes. Or if you have really absolutely no oxide or oxide creating or corrosive creating atmospheres around, then it could be also carbon-carbon. So I think you have not this one answer to this question. It's really linked to the application, to the temperature, to the duration, all the things. That's the point.
Okay, so sorry to say, but time is over. There's a red light. But I think you can also get in contact with the speakers the rest of the day. There should be no problem. So thank you, everybody. I hope you enjoyed the presentations. Yeah, that's from our side. Thank you.